Hi, my name is Nicole Trabolsi. I will be presenting our project on multimodal biometrics with enhanced mobile and IoT security. This is joint work with my partners Oscar, Yash, and Rushab. First, we will introduce the problem we're trying to solve. Next, we will discuss the methodology we use to solve it. Finally, we will conclude with the implementations and evaluation of the solution for our project. Biometrics in mobile devices are a popular feature, but it's a feature with a troubled history. One of the problems is that the mobile device biometrics don't always perform well in uncontrolled conditions, such as bad lighting, dirty fingerprint scanners, or cameras. For example, cameras held at an angle not directly at the face can result in face recognition systems not to work. Even more serious in the problem of security, for example, the iPhone 5S finger scanner was bypassed within a week of release. Similar fate was shared by the fingerprint readers in Samsung Galaxy phones. Even state-of-the-art iPhone 5X facial recognition systems was bypassed using a 3D mask manufactured by a Vietnamese company. There are also reports of kids unlocking their parents' phones since their faces look similar. We would like to draw attention to the fact that all these technologies are unimodal, which means they identify people based on a single biometric modality. Because different biometric modalities have different limitations, no modality is ideal. Therefore, we need to move past using a single biometric. Previous researchers have argued using multiple biometrics for identifying users for mobile devices. This approach is called multimodal biometrics. First, it makes spoofing attacks harder because an attacker must fake more identifying information in order to spoof the system. Multimodal biometrics can also be better in uncontrolled conditions. This is because of the quality of one modality is affected by uncontrolled conditions. We can use identifying data from the unaffected modality. Finally, the state-of-the-art mobile devices are already equipped with sensors such as cameras, microphones, and fingerprint readers necessary for implementing multimodal biometrics. There are also empirical results obtained by CSUF students. This table compares the error rates when identifying mobile devices using user-based only on face, only on voice, and using both face and voice. Notice how multimodal biometrics gives significantly lower error rates compared to using face only or voice only. The goal of our work is to use these lessons learned from implementing multimodal biometrics based on face and voice on mobile devices to bring the benefits of multimodal biometrics to IoT. Many researchers have identified many novel applications of integrating biometrics with IoT, such as healthcare and attendance. And multimodal biometrics can help improve the security of IoT biometrics in the same way they can with mobile devices. I would like to now hand it over to my teammate Yash.
Thank you, Nicole. I will now be discussing the methodology for implementing multimodal biometrics based on face and voice in the IoT. But implementing such system is easier said than done. There are three different ways of combining identifying data from different modalities. First is decision level fusion. Second is score level fusion. And third is feature level fusion. So let's go over these three. So the first is decision level fusion. It works on a majority basis. All modalities vote on whether the user is legitimate or not. For example, if the multimodal biometric system consists of fingerprint, face, and voice recognition attributes, then if two of these three biometrics determine the user to be legitimate, then the user is given access. On the other hand, score level fusion outputs match scores from different biometric types. Scores are combined into a single score, and then that score determines if the user is authenticated or not. The third is feature level fusion, which combines feature from two different modalities into a single set. And then that set is classified as either legitimate user or an imposter. Out of these three alternatives, we decided to use feature level fusion because it is associated with greater recognition accuracy as features contain more identifying information than decision or score. So let's go over this diagram, which shows a high-level overview of our system design. First, we capture the image of the face recording of the voice. Next, we remove noise from the face and voice samples, and after which we extract features from the denoise sample and then perform a feature level fusion using discriminant correlation analysis or DCA, which we will discuss in later slides. Then we classify the result using k-nearest neighbor classifier, which will determine if the user is genuine or an imposter. Now let's go over details of each step. First, we capture face image and then resize that to a 100 by 100 pixel image. And then we found that this size works well in practice. After which we extract histogram of gradient or hawk features, which describes the edge structure of the face, and also linear binary pattern or LBP features, which characterizes the facial textures. Next, we record a voice sample and denoise it using spectral gating technique. And then we extract the part of the voice signal which has voice activity. Soon after which we apply fast Fourier transformation to the resulting signal in order to extract null frequency substral coefficient or MFCCs. MFCCs are features used commonly in voice recognition, and they describe the movement of vocal cords to characterize a voice signal. Next, we use the voice and face and voice features using a new approach called the discriminant correlation analysis, or DCA. It is a technique proposed in 2016, which performs an effective feature fusion by maximizing pairwise correlation across two feature sets, and also eliminates the between class correlations and restricts the correlation to be within the classes. Now, you might be thinking why we use DCA. The reason why we chose DCA was that it solves two major challenges. First, face and voice features are measured differently and hence cannot be combined with each other. DCA does the equivalent of normalizing features before fusing. DCA also solves the problem of the curse of dimensionality, which makes the result of the combined features excessively large. DCA solves it by performing dimensional reduction. In addition, DCA also has the advantage of requiring low computational resources, which helps it run efficiently on IoT devices. Next, the fused feature set is classified using k-nearest neighbor classifier. KNN requires little training time, and it works by storing training samples. During classification, it calculates the degree of closeness between training and authentication samples. And finally, we compare the distance between the training and the authentication samples, and if it is sufficiently close, then the user is deemed legitimate. Otherwise, it's deemed an imposter. Next, I will hand over to my colleague Rushab, who will go over the implementation and the results.
Thank you so much, Yash. All right, let's go through the implementation part. Because the purpose of our project was to bring multimodal biometric to IoT devices, we implemented our approach on the Raspberry Pi Model 3 IoT device. The device was equipped with the Sony IMX219 8 megapixel camera, and also also with the USB microphone to record face and voice of the user. So everything was implemented in Python using scikit-learn, OpenCV, and Librosa libraries, which were used to implement classification, image processing, and voice processing, respectively. The evaluation was on a CSVF SG5 dataset previously curated by Dr. Goffman's students. The database contains face and voice samples from subjects of varying ethnicity captured in real-world conditions such as poorly lit places, skewed camera angles, and noisy places. Okay, let's go to the result part.
Go on, these are the results.
Yes, yeah, okay, all right. So this following table is the result of our experiment. It shows the equal error rates for the face recognition using
I think his mic is getting cut off. Rushab? I can go over the results real quick because I think his internet might be acting up a
for
little
the
bit.
measuring the accuracy of the biometric system. All right.
Okay, I'll just go over the results. As you can see, this table, it goes over two different projects. So the first row is our project, and you can see the equal error rates, which is a common metric used for measuring the accuracy of biometric systems, where lower value is better. You can see in every column, our values were way less than Dr. Goffman's previous approaches. So we used Fuse DCA, which is the least value. It's 8.04 compared to Dr. Goffman's 25.65. And face only and voice only features are also lower than Dr. Goffman's previous approaches. The timing.
Just to give you, you have about 1 minute left.
Okay, and just to go over the timings that it took to run our project, we ran this project 2,370 times, and we calculated how long it will take to use the application. 1.3 seconds were only required to enroll a user, and 0.91 seconds were to perform an authentication task. Conclusion. So our multimodal biometrics approach is used to perform secure authentication on an IoT. Our prototype was implemented on a Raspberry Pi IoT device, and results show that multimodal approach achieves significantly lower EER than unimodal approaches and the DCA approach used by Dr. Goffman. Our future plans include experimenting with other traditional classifiers, such as SVMs, random forest, and other classifiers, and also include artificial neural network to get a better gauge of if we can get better results. We also plan on using a bigger data set to see how it holds up. And if you have any questions, we'll be happy to take them.
All right, so now if you have any questions, please send it through the chat to me, and I will ask the team members. Well, people are, if anybody's asking a question while they're doing that, I have one quick question.
Yes.
You may have said it in the slides, so forgive me if I missed it, but are you doing all the processing on the Pi, or are you doing that in the cloud somewhere?
So we are doing all the pre-processing. The whole project scope is ran on the IoT device, Raspberry Pi in this case.
So how's your latency? Is it really?
So if you look at the times, let me just go to that screen. It wasn't too much. So it took, for each user, it took only 1.34 seconds to enroll one user, and like about a second to perform the authentication task, and for the user or for the IoT device to tell us if it's a genuine or an imposter.
Okay, thank you.
Yep.
Does anybody have any questions? No one's asked anything yet. So let's give people a minute or so to.
Okay, sounds good.
So someone asked if you have a demo or a video.
I don't have demo or video since it takes too long for us to run 2,370 test runs, but I do have the results for my project. So as you can see, let's go over it a little bit because I kind of like skipped over it when we were talking. But so the EER rate is basically a metric used for the accuracy of systems, and the lower value is better. So from all our samples, it only made 8.04% of error to determine if the user was imposter or genuine. And that's with Fuse dataset. If you went with just face with Hawk features, it made 16.91 equal error rates, and same with face LBP, which was 14.05. And voice features tend to be a little tricky. That's why it's just voice feature biometric approach was only 43.76% error, which is kind of high. But once we combined them with the face features, it went back down to 8.04, as you can see in the first column, 8.04.
So would you say that from these results that the face, I mean, it seems like the face is a better
face is
feature.
definitely, so it depends what features we are using. So when you compare MFCC for voice with HOG and LBP for face, it's definitely outperforming the voice features. But once you combine all three, it definitely outperforms all the just one feature biometric system. So if you fuse all three together, it's outperforming all three, as you can see.
Great. Well, I think we're out of time, but thank you very much for your presentation.
Yeah, thank you. So good morning, everyone. This is Shiva here, and my project is about identification and cataloging books from photographs using machine learning. Before starting the project, I would like to thank my advisor, Professor Anand, Without his support and advice, I wouldn't have done this project. Yeah, the purpose of this project is to recognize the title and author names from the photographs. There are many use cases we can think of where this applications we can use. For example, in library, a librarian can use this application for auditing purpose. Instead of reading the barcodes of each and every book, he can simply take pictures of the rack or shelf and find out what books are available in the rack and what are missing. This greatly reduces the manual effort, in fact. Another use case what we can think is in search engines, users can directly upload the images which has the textbooks or other books. With that, they can, a search engine can automatically search the books in the internet and add it to the cart. Again, it reduces the effort in terms of searching, selecting, and adding it to the cart, and repeating it for each and every book. So here is a quick demonstration of the application. I have developed this application on the iOS platform. So basically it works in 3 steps: click, load, and feed into the machine learning model. This application has, or user interface has, it allows users to load the image in 2 formats. Either they can take the picture or load the image from the gallery. As shown in the second image, once the image is loaded, it gives a sneak peek of the image. In our example, we have 4 textbooks in the image. Later, once user clicks on fetch titles, as shown in the third image, all the textbooks are listed. So here is another example. In this image, we have about 3 plus 3, 6 books. And on the third column, all the 6 textbooks are listed. Coming to the implementation part, this application has mainly 3 building blocks. One is recognizing the text in the image. Second, on the identification of the location of each of the texts. So this is with the use of bounding points. And thirdly, forming the titles. For forming the titles, we will have to group the words. Again, grouping of the words based on the bounding points, how close they are or whether they are overlapping on each other. Sometimes we have to use the influencing factors such as bias to improve the accuracy. As I said, there are 3 building blocks. I will go through each of these building blocks in the upcoming slides. First building block is recognizing the words. For word recognitions, I have used Google Vision API. The reason why I have picked up this Vision API is because it can identify the words or text in all angles. It can be vertical, horizontal, or slanted text. Before picking the Google Vision API, I tried my application with the Firebase ML2, but it had some drawbacks when it comes to identifying the text. So the limitation was it can pick either the horizontal text or only the vertical text, not both. Yeah, image rotation, it did not improve the accuracy in that ML kit. That's the reason I went back to Google Vision API. Here is the example I have shown for bounding points, which is nothing but the word's location in the image. For example, in the image I have shown, we have a word called Steve. When we use Google Vision API, it fetches the word on the description part and the bounding points, which is nothing but X and Y coordinates of each of the corners of the text. If we see this image, all the 5 words Steve Jobs by Walter Isaacson, they are in one line. In such cases, it's very easy to form the title, but that's not always the case. For example, in this second image, we have introduction to as one column, and there is another word algorithms in another column. There is no overlapping in this vertical image. However, if we pick the word Corman or Rivestein or any other word, we can group them together because there is at least one word overlapping with the another. That's exactly shown in the case 1. Let's say we have picked the word text 1. With that, we are seeing text 3 as the overlapping word. They can be grouped together. Instead of stopping it right there, we can use the text 3 as another word and find out what are the other overlapping words with that. So this is where grouping of the words with the overlapping helps. However, in the second case, text 4 and text 5, there is absolutely no overlapping. In such cases, this will end up with the 2 titles rather than 1. For developing, I have used Google Vision API as the ML API. Then for the front end, I have used Flutter, and as a programming language, it's Dart. Coming to the performance evaluation of the application, what I have seen is when the images are very close, the accuracy ranges from 90 to 100%. Yeah, it's not always 100% because there are chances that words may not be overlapping. Again, there could be chance that textbook would be in a slanted format or in different orientation. In such cases, accuracy degrades. I'm still working on the horizontal or distance images. Yeah, so I'm still I'm yet to evaluate the performance in those areas. Another interesting thing what I have seen in this application is some of the words which may be human unreadable, but using this application, it clearly captures even such words in the title. Coming to the speed, it's pretty much a real-time identification. Hardly there is 3 seconds to 5 seconds of difference from the time we feed into the application and see the result. Yeah, it works with all orientations, whether it's horizontal, vertical, or slant. But yeah, so in some cases, performance or accuracy is slightly less. Again, there's a scope for further improvement on this. Let's say if books are totally unorganized, we can still fine tune the model. These are some of the image sets I have used for a testing purpose. As you can see, image can have one textbook or multiple textbooks and in a different orientation. Yeah, that's all I have for today. If you have any questions, I'll be happy to answer.
All right, thank you very much. So now if you have any questions, please in the chat, send it to me and then I will ask. So let's just give people a few minutes
Yeah,
to ask some questions.
Mhm.
Do you have a demo or anything like that that you can show or?
I haven't prepared a demo, but yeah, the image snapshots I have given it in this slide.
Mm-hmm. Do you plan to release the app that can be tried by people?
Yeah, definitely. I will do that.
Okay.
Yeah,
if you
but
do,
I need to
look,
Mhm.
sorry about that. Go ahead.
Yeah, I need to see how it works in iOS. For now, what I have done is I loaded the app into my mobile by connecting the iPhone device to my laptop.
Mm-hmm.
For the release part, I don't know how it works. Yeah, I need to find it out.
What about do you have a Git or anything like that you could share? Going to?
Yeah, I will definitely share that.
Okay, great.
Yeah.
That'd be great. So does anybody have any questions? I don't see anybody ask anything. Let's wait another minute or so and see if
Yeah.
anybody asks.
Definitely.
We're ahead of schedule anyway, so we can wait. So you said that, I have one question. You said that you had 90% to 100% accuracy.
Yeah.
What would happen in the cases where you were in that 90%? Would it kind of garble words, or would it just not guess the word at all? Or
Yeah, in such cases, what will happen is instead of grouping them as one title, there will be two titles split into two.
okay.
Yeah.
And then somebody did ask, how did you overcome any issues?
How did I overcome? Yeah, so it's purely based on the testing. As I said in the beginning, I had to find out how we can continue finding the overlapping words rather than stopping at picking one word and stopping it right there. So it's purely based on the testing results. So,
okay. So
you
I
and I
guess,
tried
like,
with.
correct me if I'm wrong, for the person who asked, but I guess what he's asking, like in the cases where you did have like some error, do you have any plans on how to overcome that in the future, or do you have any plans on how to deal with that?
Yeah, for unorganized books, that's really a challenge how we can use this application. Yeah, so for now, I'm sticking to either horizontal, vertical, or slightly slanted books. Again, slanted
Okay.
books may not give the good accuracy.
Okay, great.
Yeah.
So we have time for another question or two, if anybody else has any questions. Somebody commented they liked the idea for taking inventory. So it was a comment. They said they liked the idea.
Oh, great.
I agree.
Thank you.
I like the idea a lot too. So it's good. Okay, I think that's it. So thank you very much for your presentation.
Yeah, thanks again for the opportunity.
Good morning, everyone. My name is Brian Tran, and I have my teammates Danny Vega and Johnny Tran, and we are from the Electrical Engineering Department. And our project is called the All-in-One Window Buddy. Okay. So window curtains allow light to permeate into the room to be 15 being a big issue. It would be ideal if the window curtains can automatically be opened and themselves right home late at night with the window curtains wide open, exposing the interior of their home to potential thieves who know what they have and that they're not home. In addition, there are homes that have many windows. In the morning and evening routines can be streamlined for people living in those homes if they didn't have to worry about opening and closing window curtains. So for the all-in-one window buddy, the objective is to build a device that can be configured to open and close curtains in a variety of ways, depending on what the user needs. One of them is wirelessly through your smartphone. Another one is automatically through the environment via light sensors. Another one is through a clock function where the user can preset a time for the window curtains to open and close. And also you have an option of just pressing a button to open or close window curtains.
For the going project description, we have for the component one. So this project will be implemented by having a servo motor with an external power source that will be hooked with to the curtains, and an RF receiver would activate the power to the motor. And for the component two, And this RF signal would come from an RF transmitter hooked up to an Arduino, and the Arduino will be hooked up to the light sensor, boost bottom, Wi-Fi board, and finally an LCD will working clock. Whenever current conditions are met, the Arduino activates the RF transmitter, sending a signal to receiver to open and close the curtains.
Okay, so the IEE standards that are used for the all-in-one window body is the IEE standard for fuzzy to basically automatically open and closing the curtains. And then another one is the IEE guide for application of electric motors in class 1, division 2, and class 1, zone 2 hazardous locations, since we are using a DC motor to open and close the window curtains. And then we have the IEE standard for information technology, local and metropolitan area networks, as well as the IEE standard for information technology, telecommunication, and information exchange between systems, because we are using RF transmitters and RF receivers to wirelessly communicate with each other, as well as have the curtains communicate through the smartphone as well wirelessly.
Okay, so I'm gonna explain the block diagram and circuit schematics. So Brian, can you skip over to slide 8, please? So this is an oversimplified look at the schematic. So on one side, we're going to have on the right, we're going to have the transmitter. So this is where all the peripherals are going to be attached to the Arduino. Basically, its intention is to receive an on signal. So if there isn't enough light coming in the room, that's going to trigger the Arduino to send an on signal. Also, if you want to push the button, control it manually, that would also send an on signal. So what the Arduino does is then it captures that, sends it over to the RF transmitter, and the RF transmitter will send it over to the RF receiver. And the RF receiver then sends that message over to the Arduino, and then thereby turning on the motor, causing the curtains to open and close. And then I think Johnny will go over the actual setup of the window.
Okay, Brian, can you move all-in-one window PuTTY setup slide,
Okay.
please? Okay, so as you guys can see right here, so I had to set up current with the boost bottom right here. So as you can see, the current fit with the motor device and boost bottom. And I had to hook up the string with the current rings and the motor. And when the motor spinning, it will control the movement of the string, and so it can open or close the curtains. Okay.
And then we have some videos on showing how it works in motion. And this is how it works when we're closing the curtains. Okay, so right now, I'm going to just give you like a little closer look on the overall setup for the push button light sensor. And now I'm going to talk about the constraints. So the constraints that we have while building the all-in-one window buddy is figure out a way how to predetermine when a curtain stops like rolling up or stops rolling down, which in this case is like closing it by going all the way to the right, or opening going all the way to the left. Another constraint is figure out a way to create code in Arduino that will allow us to interact with more than one current at once. Another constraint is to figure out a way for a circuit to communicate with the smartphone, notify a user if the current is pulled up, pulled down, and figure out how to get the clock function operate properly with respect to restricted I/O ports on the Arduino board. Okay. So the results are that we did manage to successfully implement a wireless communication between the RF transmitter and RF receiver, and we are able to implement the push button so that the currents can be open and closed manually. However, we did not successfully able to implement the clock function to have the window curtains automatically open or close through a preset time that the user sets.
And a reason for that was when we realized just how many inputs the clock, so the Arduino itself has an internal clock, but in order for it to be constantly on, you need another peripheral to be able to continue powering the Arduino. Not only that, but we realized that the user should have a way to set the time on the Arduino without having to connect it to the computer and pull up the Arduino software and then doing it that way. So the only way we would be able to allow the user to do it externally was to add LCD screen and also some push buttons. But that alone was already taking up most of the pins on the Arduino. And from the very beginning, we wanted to be able to simplify this project as much as possible. And originally, we actually wanted to do just one Arduino, but that was not possible. So we ended up using two, and the idea of adding yet another one we felt was not good for our intent, at least. And we also had a few problems going down the route of doing the Wi-Fi portion of it. Johnny was more in charge of that. Perhaps he can speak on to the problems that we had with that.
Okay, so so we did not so successful for the opening and closing curtain using the smartphone, and I have done is the code, but it's so complex to create the app on the phone to opening and closing the curtains. Okay, Brian.
Okay, but despite all of those setbacks, we did prove that it was possible to have two options for the user to open the window curtains, open and close the window curtains through more than one way. I've noticed in many projects that I've seen, DIY projects, for example, that usually like they only focus on one function, but then with the all-in-one window button, we proved that you can have more than one function working when we open and closing window curtains. The all-in-one window button got us a chance to not only hone in our knowledge, but also gain more knowledge when it comes to circuit designs to get the all-in-one window buddy working in its current state. And then also, the all-in-one window buddy allows us to take a deeper look at areas of interest and build something we initially never thought possible. And it also helped us to strengthen the development of our critical thinking and problem-solving skills that will enable us to further our careers as engineers in the future. And then these are the references that we use throughout the project to get it where it is today. And with that in mind, that is the end of the PowerPoint presentation. And if you have any questions, please feel free to ask away.
All right, thank you very much. Yeah, if you have any questions, please shoot me a chat and I'll ask. I just have a comment. I think it was a good project. I think you probably could have this could have been a collaborative project, maybe with like a CS student to include maybe some IoT part to it. Maybe that would have eased some of the issues you had, like setting the clock and things like that. Just a comment. Maybe in the future, if this project continues, they could collaborate with CS or CPE.
Okay.
Any Any comments or questions? So let's just give them a few minutes to type any questions they may have.
Sounds good.
So I have one other question that just kind of popped in my mind. You guys are using an Arduino Uno.
Yes.
Correct.
Did you consider like a Mega or maybe a more powerful Arduino?
No, we actually didn't consider that. We were trying to. Is that more expensive?
Yeah, it is, but I mean it's not much more. It's not.
No.
It has more ports. It could handle more current supply. So I would, and it's faster. You know, the faster clock and whatnot. So, or even another microcontroller. Did you guys didn't consider maybe a Pi or something like that?
Initially, actually, I had wanted to always work with an Arduino, but I hadn't before. So coming into this project, one thing that I wanted to make sure is that out of this project that I was going to learn, not only be able to implement the project, but learn along the way. And the Arduino had always piqued my mind, my interest. And so that's why we went with the Arduino. Unfortunately, we didn't have enough foresight to see that the clock and the LCD screen was gonna need so many inputs. So by the time we got to that point, we had already ordered everything, and because of the current situation, to try to order more, the equipment wasn't going to arrive in time.
That makes sense. All right, thank you. Any other questions in the chat? I don't see anybody asking anything. So somebody's asking, did you have to address issues for the weight of your string or curtains? So did you have to adjust for like the different weight, not wait time, but like weight and heaviness of the curtains or strings?
No, we had it from the original. Kind of wanted to do just a demonstration of the potential that the Window Buddy had. We chose a relatively small setup, as you saw, and we figured that the motor that came with the all-in-one kit was more than powerful enough to be able to pull on the strings. But this is something that can definitely be expanded to. I mean, in my house, I have huge windows, and it would require much bigger motors. So in that case, I guess it would be great to use some of those other Arduinos that can handle more current. But no, for this one, we wanted to just keep the scale really small, just for this purpose of being able to present it. So this project has a lot of potential to be able to expand more. One of the things that we had one of the things that Brian mentioned was we were looking into being able to control more than one window at a time.
Yeah, somebody's commenting to turn on your screen. He said he could hear you but not view. Another person asked, what's the total cost for the unit and what is the life cycle?
The total cost was around $570. Roughly around $570. That's for the total cost of the entire setup. And to be honest, I don't think I've looked into like the lifetime of the all-white Window Buddy. But I think that it could have a pretty good lifetime, especially if you expand it to allow more current to be used for this project. So.
And then somebody just commented, very good, which I agree. It was a good project.
Thank you.
All right. I don't think there's any more questions. So thank you very much. And
so most of the people are familiar with drones, whether they are quadcopters or the ones that military use or the ones that people use for fun. But sorry, but are they familiar with this type of drones? I'm not sure. So this is Abdurazak Al-Thuwaini from the Electrical Engineering Department, and I'll be presenting to you guys the Robotic Bird. So this project is about a bionic bird that flies by flapping its wings, which makes it look like a real bird. And it's not a regular kind of bird. It is a peregrine falcon. This is not a toy to enjoy. It has an actual mission. The whole idea behind it that it mimics real life, and the peregrine falcon, especially for birds, is the most feared predator. So the main idea behind it is instead of using quadcopter or rotor style drone, which birds tend to habituate with, those types of drones, in contrary, the Robird is designed that birds don't habituate and get used to it because it's in their natural predator. This project applies an ornithopter style and that lift works because it's extremely light. There is an internal mechanical mechanism inside of it that allows it to flap, and it glides just like a real bird would. It is controlled by an RC controller, which means it is piloted, not autonomous. The body design is nylon composite, and the wings and tail are made of polyfoam, so it stays extremely light and extremely strong at the same time. The battery is standard LiPo battery, and the endurance is about 12 to 20 minutes. The overall weight is between 450 and 750 grams. The distance that could go is up to 2 kilometers of range. It has to flap 2 beats per second with its wings. It can go up to 6 beats per second. It glides as well. When it's in glide mode, it gets enough lift to keep it in the air just like a real bird. It is going to be mostly used in airports to prevent airplanes from bird strikes. I'll show you guys now some examples of bird strikes that happen in real life. So one of them is this. The other one. Now I'll go over the design. So here's an overview of the design, and here's a 3D model of it. And the gearbox. This is a 3D design model of the gearbox. So basically, we're converting the rotational movement to a linear movement, so the wings can go up and down. And here's the 3D printed design that I'm using. As you guys see, 2 gears and 1 for the motor. And here are the components that I'm using: a DC motor and a speed controller, servos motor for the tail to rotate, and the batteries, and the DC power, big tail cables, charging cables, and the camber tolling, gears, pinion gears, ball bearings, and a mini FPV camera, and a mini real-time GPS tracker, and my transmitter and the receiver. And here's the bill of material, which you guys see, it's nothing, like 250 the total. Sorry. And yeah, this is the timeline, and I'll show you a quick video.
so I don't know how it is for everybody else, but it's frozen on my screen.
Well, what was it not shown? Well,
Yeah, actually, we can't see your screen anymore, and it froze on my screen. People are saying it froze on their screen as well.
oh, okay. Let me just retry to play the
I think
video.
you need to share your screen again too.
Okay. Do you guys see the video now?
Yes, I can see it.
Just replay it from the beginning. Okay.
Yeah, that's working now.
Yeah. Yeah, so basically, this is the thing I'm trying to make, and I actually already made it. I'll show you some pictures of my project right now. Let me go and share pictures. So this is the bird that I made, but due to coronavirus, I was gonna build the whole design using 3D printer, but I couldn't do that because campus is closed and I have no 3D printer. So I made the body from foam, as you guys can see. And I used an umbrella cover for the wings. And this is my little camera here. And that's it.
All right, that's great. I have a quick question. Were you able to ever test it?
Well, as I just said, due to coronavirus, most of the open areas are closed right now, or like we're
Yeah.
not able to go out. I'm just waiting until everything goes back to normal. Then that's the first thing that I'll be doing, just to test
Yeah,
it.
yeah. That's why I was asking because I was
Well,
doubting that.
I have tried the mechanism, and everything works perfectly. The tail, the wings, and I've tried it to glide, and yeah, it did glide actually.
Somebody made a comment saying it looks good, and I agree. Did you have a mechanical background, or did you have any help from a mechanical engineer? It
Well,
seems,
for this project, even though I'm doing electrical engineering, but it's mainly focusing on the aerodynamics and the mechanical engineering stuff like the gears ratio and how to find the gears ratio, because you need a lot of torque for this project so you can move the wings. So I did a little bit of research on those topics like the aerodynamics and the gears and most of the stuff like that. And yeah, it took me a while to understand them. Then I had to apply them perfectly.
oh wow, that's pretty impressive that you're able to do that on your own. That's really good. Any other comments from the participants?
Oh
Or
yeah, and
questions?
I made the gearbox by myself. I had to teach myself how to use the software, 3D modeling software actually.
Wow, that's impressive. Yeah, and a lot of people are saying good work, and yeah, you did a great job. Let's just wait to see if there's any other comments or questions. Just wait a minute. Yeah, everybody's saying very impressive, good job. There's a lot of congratulations there.
Thank you.
So let's just wait a minute and see if there's any other questions. So somebody asked, how much did it weigh with the electrical cables added?
Well, I weighed it yesterday and was about 720 pounds, 20 grams, sorry, 720 grams.
And then somebody asked, is that a camera? And I believe it is, yes, it is a camera.
It is a camera. I'm using a really mini camera that's connected to my iPhone. And I'm using a mini GPS, a real lifetime GPS.
And then somebody said, are a lot of the projects interdisciplinary, like CS working with EE? And yes, they are. I know for a fact a lot of them are. I know this particular project isn't interdisciplinary. You did all the mechanical work on your own.
Mm-hmm. That's true.
But yes, a lot of them are interdisciplinary. And then he also commented that he loves it. He thinks it looks awesome.
Thank you very much.
Another person asked, do you anticipate this design with different materials to fly?
Sorry, I couldn't hear that.
He's asking, do you anticipate using different materials when you actually try to fly it?
Well, I was gonna use the what's called the 3D printed materials for it, but I couldn't use it because of the campus is closed. But right now, this is all what I have. So
yeah. I guess what he's asking that if you could hypothetically, you would use different materials, and the answer is yes, you would 3D print it.
So the plan was to use another material, like what's called I forgot the name of the other material. So basically the body was supposed to be 3D printed instead of the foam.
Yeah. So does it answer your question, Danny? You could just hit yes if it does. And then somebody asked how much it weighs. We already, but I don't remember. How much did it weigh again? Can you just repeat?
720 grams.
720 grams. And then somebody asked, what's the motion controller that's being used?
Motion controls. I'm using. You mean for the tail to rotate right and left and land and take off?
I'm not sure. Jose, can you clarify a little bit more on what you mean by motion controller? Just give him a second to type his. So while he's typing that, I think this would be a great project. It could be very interdisciplinary. You could have EE, ME, and probably CS on this project as well. If it's anticipated this is going to be continued in the future. I guess he's asking what computer are you using? It's like an Arduino.
Well, I'm not using any kind of microcontrollers. I'm only using the receiver and the transmitter for a regular RC planes or cars.
Oh, okay, so you're using an RC controller.
Yeah, RC controller. Yeah.
So Danny clarified. He said, since you're not using the original material, do you anticipate that this model would fly?
Well, I tried it yesterday, and I've checked if it glides or not, and it did glide. And I've seen if the wings are applying any air, like pushing any air like down, and yeah, they did push some air down. So if I try it maybe one day, I think it will fly.
Yeah, and then your advisor, Dr. Chang, said yes, this could be a multidisciplinary project, and I agree.
Mm-hmm.
All right. Any other questions? Somebody's asking, is that an ultrasonic rangefinder in white? No, that's a camera.
No, that's a camera.
Yeah.
That's a really mini camera.
It's a mini camera, yeah. Any other questions? We have time for a couple more, if anybody else. Like, your project was great. So somebody's asking, have you thought about using LiDAR or sonar for obstacle detection?
Well, I thought about that, but I don't have enough time to focus on these things because I had to teach myself and read more about the other topics that we never learned, especially like in electrical engineering, like using the software and the aerodynamics and the gears. So I dedicated most of my time just focusing on these things.
Yeah, and I think that's why I would make a great multidisciplinary.
Yeah, and definitely in the future, I will do some modifications and add some stuff to it, make it more professional. And
then somebody, Elizabeth asked, do you know if any airports use this technology? Like you showed a FISTO version. Do you know if they use those currently?
Well, from my experience and like my opinion and my researches, nobody has used it yet, but it's like a plan for the future to be used.
Okay.
Yeah.
And then Jose commented that Titan Rover is a great resource to learn how to use all kinds of sensors and actuators. So just a comment. Yeah, because that's a ME group. Actually, it's multidisciplinary. Titan Rover has ME, EE, CPE, CS, all different types of people working on it.
That's great.
We have time for maybe one more comment, one more question. All right, no, I think that's it for one more comment, one more question. They're asking how much. I think it was like around $250 if I recall correctly.
Yeah, it's $250. That all what cost me.
Yeah.
Yeah.
All right, well, thank you very much. That was a really good project.
Good morning, professors and fellow future engineers. My name is Abdallah Abdul Rahman, and today my partner Jesse and I will take you through our smart wheelchair project. As engineers, our main goal is to make the lives of everyone around us a bit easier. Growing up, I had an aunt who was partially paralyzed. It was difficult for her to get around and always needed assistance. So you can say she's the inspiration to our project. So I'll start off with our abstract. To create an eye-controlled system which will allow movement of the patient's wheelchair, depending on the movement of the eye. This system can help enable those who are physically unable to move, which can reinstate their means of self-reliance and reinstate their confidence and happiness. The purpose of this eye-controlled wheelchair is to completely enable a paralyzed patient, elderly, or anyone using a wheelchair to make their life more accessible. These two pictures are pictures of wheelchairs that are currently on the market without the eye-controlled system, just regular mechanical wheelchairs. You can see the cost, it's from about $2,000, like that's the cheapest, and then you can go on up. This project will be designed to enable wheelchair users to move without the struggle of being pushed around, nor exerting energy by wheeling oneself. This will be done through an eye-control system that consists of a camera module, microcontroller module, and a motor module, all working simultaneously together. So over here, we tried to do this just on a mini little car just to see if it will work. And then moving on, we would do it on an actual wheelchair. Jesse, you can go ahead and start with the standards and constraints.
All right, so these are a couple standards that we were able to use to come up with our project. So the first one would be the standard for the sensor performance parameters. The next one is the guide for design for the battery energy, the systems, stationary and mobile application, and electrical power systems. Then the next one is any standards for wheelchairs, the electrical wheelchairs to be exact, and that one tells you the exact, basically the limits on the speed that you can have for the power wheelchairs. And then we have the international standard for informational technology. So in the next one, we have the constraints. So the first one is obviously safety. The device should not be able to injure users. It will have safety override functions in case the eye tracking malfunctions. The environmental is that it should be able to operate for everyday use while keeping the power consumption at a minimal. And economic, the price should be affordable compared to other competitors. All right, so the project design, this is our block diagram. So our smart wheelchair has been designed to provide navigation assistance to the user. This has been achieved through our eye tracking force sensing resistor and sonar sensor modules. Our modules will first be independently constructed and tested, then assembled together through our microcontroller. The microcontroller will act as our main storage and input-output device for all our modules. With the combination of our modules, we assure collision-free travel while aiding the performance of specific tasks and autonomously transporting the users between locations. So this is our circuit schematic diagram. This is all the components that are going into creating our system, eye tracking system. And this is our motor schematics. This is how the left motor and right motor will be controlled. And to the right, we have all the motor logics that are being used to control pretty much the wheels. And then this is our progress. So for now, we have the face detection. There's an example that we put together, Shakira, and then the sonar sensor. That's what's gonna help with having the collision-free, pretty much wheelchair. And then the pressure sensor will act as the wake-up call to turn on the system. And then the Arduino is what we actually had to use because of all this coronavirus thing. We had to come up with something to pretty much put together. And then instead of a wheelchair, because all this COVID-19, we weren't able to actually meet with people to get a wheelchair. So we decided to do this on a RC.
And for the face detection, we used OpenCV, the program. It's a machine learning program. So once it detects the eyes of the person on the chair, and then once the movement of the eye, so if it goes right, then the OpenCV tells the microcontroller to tell the motor to go right, and then so on and so forth. So we used the Arduino and we programmed it. So once, say, for example, if you blink once, then that will start for you to go forward. If you blink twice, it'll stop the chair, and so on and so forth.
All right, so this is our bill of materials. Everything that goes into building our system came up to the total of $334 with 38 cents.
And that's without the actual wheelchair. So we could build this system and implement it onto any wheelchair, but it also depends on, because some wheelchairs don't let you have access to the motor. And this was our timetable. So for our results, working on our project was very challenging at first. We first started with the machine learning software, OpenCV. I had a difficult time trying different methods on installing and learning the software, but towards the end, we were able to understand and utilize the software for our purpose of eye tracking. Moving towards our hardware was much simpler and understandable for us. We were able to construct our force sensing resistor and infra sensor models with little difficulties. But due to the COVID-19 situation and limited lab access, we were only able to construct our modules separately. Although we had limited access to the lab, we were successfully able to construct and code all our main components for our smart wheelchair. This project was carried out to fulfill the requirement of the senior design project of Bachelor's in Electrical Engineering. Smart wheelchair was chosen to be done as it incorporated designing an embedded system that was real-time and due to the sensor that was to be used in it. Most modern-day technologies use sensors such as electrometer, gyroscope to take interactive input, and in this project, we also have tried to make the robot interactive and respond in real time. Also, we wanted to get a better understanding on the use of machine learning program OpenCV, the FSR, sonar sensor, the accelerometer, Arduino ultrasonic sensor, and its working in detail. And we also wanted to develop a fast and real-time project that can help people. These conditions made the smart wheelchair a suitable project for us. Completion of this project needed sheer determination as there were many things that could go wrong. Though some difficulties arose due to the current epidemic, coronavirus, our team was able to understand the scope of the smart wheelchair project and carry out the electrical and software design of the project. However, the mechanical design meant a lot in this project as well, creating a mechanical structure to prove to be difficult task as our group wasn't able to work together in a lab. The smart wheelchair has some limitations, which we learned while through the course of this project. At last, the smart wheelchair project was came very close to the adaptive design philosophy. And so some of the things that we came across was, for example, OpenCV. Our other option we could have used was MATLAB, And for our Arduino, at first we tried to use the MSP 430, but we had difficulty with that. So we ended up ordering an Arduino. I'm gonna go ahead and show you guys a video of what's on the market right now, an example of how it would work. You guys see the YouTube video I have?
Yeah, we can see it.
Okay. So as you guys saw in the video, he wasn't using his hands at all. The person in the wheelchair is completely paralyzed. In front of him, he has a camera, and the camera detects his eye movement, telling the wheelchair where to go. And also they added the tablet, so that way it doesn't block his vision, so that way he can see what's in front of him still. So that concludes our project, and if you guys have any questions, go ahead.
Yeah, if you have any questions, please type it in the chat and I'll convey your question. I just wanted some clarification on something. Maybe you did mention it, but maybe I missed it. So was OpenCV done in an embedded fashion on the Arduino, or did you do it like in the cloud and on a laptop, and the Arduino was communicating?
Actually, our third partner is the one who worked on it. Michael, he's not here right now, but I have a good background of what he did. So he actually worked on OpenCV alone, and he understood the program, made the program work, and then he added it to the Arduino. So it wasn't through the Arduino itself. It was through the program, and then we, through the cloud, connected it to the Arduino.
Okay, thank you. And then Isaac asked, what would happen if someone blinks too many times? Does it get accidentally read as an action?
So that would be like our emergency. So say, for example, the camera isn't able to detect the eye movement, or there's too many blinks. So in that case, we go to the emergency, which just stops at the wheelchair. And then you can override it, because usually you would override it, and then you would able to mechanically use the wheelchair in case of emergency.
And then Dr. Chang, your advisor, made a comment. He said the design is quite complex. The end product is practical and useful with face recognition capability, but the unique thing here is eye control.
Yes, thank you, Professor.
Any other comments or questions? We have time for some more. We're ahead of schedule, so.
So there also, let me add another comment. So there you could go multiple ways with this. So for example, there's another thing on the market right now where, so it's also eye controlled, but instead you're controlling a mechanical device that controls the joystick of the wheelchair. So say you have like a regular wheelchair, as you see here in the poster, this one. So what you do is you do the whole set. You have the eye tracking, the Arduino, everything. And then you add a mechanical device on top of the joystick, and then it controls the joystick for you instead of you controlling it with your hand yourself. So that's another idea for it.
I know the COVID situation has made things difficult to make demos, but did you by any chance, were you able to make a demo with the toy car by any chance, or?
So as you see over here, so this is what we have, but we didn't have a video of it.
Okay.
But so we build the circuit, and then it would move the actual control, the mini car. And then as you can see over here, this is how the helmet would be put and stuff. But this is, we worked with what we had, and this was in the beginning of the project. And then, like, due to the corona, we actually, all our stuff got locked up in the lab, and we weren't able to get it back.
I just want to comment that I think this is a great project.
Thank you. We
Yeah,
really hoped that we could see it all the way through. It was something that not just for our senior project class, this is something we would actually want to do in the future, but just due to the situation.
yeah, I know it's unfortunate. Several people, somebody commented nice, meaningful, and very needed. And then Taylor commented great poster design, which I agree. That's a great poster.
Thank you very much, guys.
Well, it doesn't look like we have any more comments. So Jesse and Abdallah, thank you very much for your presentation. That was a very good project.
Well, this is a smart helmet. I'm Rafael Garcia.
I'm Elena Logan.
Taylor Reed. And this is our senior design project. Let me go to the next page. The purpose for this project was to create an interactive helmet for motorcyclists. Essentially, we wanted to ensure that they had a sense of security every time they were on the road, just to provide legal and physical protection. Being that, especially here in California, a lot of motorcyclists are generally in a car accident due to the heavy traffic conditions here in Southern California. So we wanted to make sure one of the main features of our smart helmet was to provide audio and video documentation for their legal safety in a court of law. Essentially, our project provides a sound system. We provided a HUD for providing rear view video. This way, the rider can see what is behind them, and it's displayed in front of them through a transparent film. We wanted to provide weather updates, time and date updates through the 16:2 LCD screen. And we made sure that we were able to provide documentation through a dash camera. We also wanted to provide easy access to the Raspberry Pi to the user. This is why we implemented a touchscreen. And overall, these are one of the main ideas for our project.
Going off what Raf was saying, these are the concepts of design. We have our front camera, our one-way audio, a breathalyzer sensor that will tell you whether or not you should be driving if you've been drinking, the rear view camera, weather updates, LED lights for alerting, LCD screen for interfacing. And then this is our implemented ideas block diagram. As you can see, we have everything connected to either the Raspberry Pi or even a Raspberry Pi Zero, which both are connected to a battery pack. This is the purpose of the concepts. For the one-way audio, it will allow the motorcyclist to listen to GPS instructions and as well as music. The LCD screen will show the weather, date, time, and the breathalyzer reading. The heads-up display will display the rear view camera feed. The LCD touchscreen allows user-friendly interface directly to the Raspberry Pi 4. The LED alerting will allow vehicles from behind to watch out for the cyclists on the road. And then the dash camera will record and store the footage of the front view of the motorcycle.
Now, going into the first topic is the one-way audio. So I'm just going to discuss the manner at which we conducted it. So you use your smart device, it connects via Bluetooth to your Raspberry Pi, and then it forces the audio out through the auxiliary port. And then you could see here the actual connections is the power amplifier, and it outputs directly to a speaker. And the actual outcome of the one-way audio is the first problem that we had was we originally wanted to do two-way audio where you can receive and send out audio via, like if you were going to take in a phone call. But sadly, when you are trying to implement the actual idea via Bluetooth, it drops the signal entirely, and it just lets you pick up the phone call as you normally would. So we just decided to just implement the one-way audio via your smart device, and then you can listen to music, GPS instructions, and also if you're a fan of podcasts, you can listen to podcasts too.
We provided a QR code for each video on our YouTube channel. So if you want to check out our videos, you'll be seeing QR codes for each one of our concepts.
Yeah. The next idea that we implemented was the LCD screen 16:2. So this is running off of Python. It gives the breathalyzer readings, and by using, to get the actual breathalyzer readings, you're using an analog to digital converter because the analog signal gives us better readings overall than the digital signal. And there was a lot of times where it was very fidgety. So we decided to just use the analog. And then that analog signal is taken into a logical bidirectional logic converter, which converts it from a 5-volt signal to a 3.3-volt signal, in which it can be read onto the Raspberry Pi directly. Because the Raspberry Pi cannot read 5-volt signals, it can only read a 3.3-volt signal. And then we're also using the touch screen to allow the user to, when they want to get their breathalyzer readings, they could just press the button at a certain time and they can have the readings that if they're intoxicated or not. And also on the LCD screen, we have weather updates for a specific city. On the Python code, it has a set city that you put in. We designed it for Fullerton. You can change the city whenever you want, but you would have to go into the Python code to actually edit it. And it's using an import of the Open Weather API, which is an application programmable interface. And that lets you have the weather and wind and maximum temperatures and minimum temperatures and whatever you need. And also gives the time and date functions. And the LCD outcomes, we originally were trying to do a speedometer and have the speedometer reading on it, but there are a lot of issues due to COVID-19 being an issue, hardware delays that we're having issues with. So we decided to drop that, but we were thinking about putting a speedometer on the actual helmet too. And again, this is using a Python script, and it's looping through it every 3 seconds, and it's displaying the alcohol sensor, whether it's you're able to touch screen or touch it, the weather updates, and the time and date, as stated before. And please, if you need to, you can use the QR code if you want to watch the video. Oh wait, sorry, this one we are actually you're gonna see the actual video. In the little cap, there's a little bit of alcohol. It should be able to sense it. So there are some safety elements for the project too. Also, we have the LED lights, just a very simple looping through a Python script, turning off and on the LEDs, and yeah. This is the overall schematic. In the top left, you see the LCD screen. Bottom left is the power amplifier, which is taking the analog signal or the auxiliary port and pushing the audio through the speaker. And then on the right side, you'll just see that the actual connections for the breathalyzer and the touch sensor.
So next we have the heads-up display. The heads-up display allows the driver to have visual of the rear and not have any obstruction of the view. The rear view camera is connected to the Raspberry Pi and displays live footage onto the LCD screen. There's a reflective film on the display so it's easily to be seen, but also it can be seen through. We want this so that the motorcyclist is able to see what's behind them without having to turn around or look back. And also with the heads-up display, it allows it to not totally obstruct their view because sometimes there's things in the way, but this, you can easily see through it. We were able to do this through a Raspberry Pi Zero and an LCD screen that's connected directly to the Raspberry Pi Zero because we wanted it to be kind of separate from and not dependent on the Raspberry Pi 4, so it has its own implementation. And we were able to test it, and it was able to be seen through during the day and as well as at nighttime. There's QR codes for some demos for the both.
For the 5-inch display, we just essentially wanted to create easy access to the Raspberry Pi 4 features. We wanted to make sure that there was no need for the mouse and the keyboard, being that this was going to be mounted on the helmet. We just want to create easy access directly to whatever needed to be accessed on the Raspberry Pi 4. Initially, the touchscreen itself removes the need for a mouse, but you still need a keyboard. So we had to configure a touch button on the top right corner here. You'll see it. And in that touch button, it creates a drop-down keypad, which allows the user to, with the use of touch, they're able to type in whatever they need. And therefore, we were able to get rid of the keyboard aspect as well. The front view dash cam, again, the central aspect of this was to provide front view video and audio storage, being that motorcyclists are more prone to being in an accident. And at the same time, understanding that it creates a peace of mind for the rider itself. The footage is stored onto the Raspberry Pi, which is creating easy access to the stored files through a micro SD card. And originally we were going to use a webcam. And the issue with that was that a grand majority of webcams had to be manually focused. So we wanted to transition to something that would autofocus and provide high quality video, which is why we transitioned to a dash cam. And again, the QR code is there for anyone that needs it or wants to see it.
Here are our references. The first QR code is our actual YouTube channel, and the other 4 links are other helmets on the market, which are very expensive compared to ours. And in conclusion, overall, although we had some setbacks due to COVID-19, we were able to prove most concepts individually. We were able to provide ideas that enhance the experience and safety of the motorcyclist. These concepts are up for optimization, which will create a more effective helmet for all motorcyclists around the globe. This concludes our presentation. If anyone has any questions, we'll be happy to answer them, or feel free to send your question to our email address, which is at the bottom.
All right, thank you very much. If you have any questions, please type in the chat and I'll convey it. One question I have about the heads-up display. So the LCD screen, is it going to be just in front of them, or is it actually mounted in the helmet? I think that was unclear.
The heads-up display, the LCD screen will be mounted kind of in front of the visor so that it could, or in front or behind. We haven't really gotten that because of COVID. We weren't able to attach it, but we're going to put it either in front or behind so that it's able to reflect onto the visor on the film.
Okay. Some comments. Great project. Yeah, I think it's a really nice project. Dr. Chang commented, great teamwork, good design with multi-functions and applications, well presented.
Thank you, Dr. Chang. Appreciate it, Dr. Chang.
I agree too.
Thank you, Professor.
Thank you, Dr. Fowler.
I have one question. Did you consider, I know the COVID thing is preventing, but did you ever consider maybe some IoT features like communicating with the cloud and maybe a mobile app or something like that? Was it ever considered?
Yeah, I would say that it was. We actually didn't provide our potential ideas block diagram here, but we definitely wanted to integrate other aspects as well. We actually thought that through a application would provide the easiest accessibility to whatever aspect you wanted on the helmet originally. But due to time constraints, and we just wanted to kind of focus on primarily enhancing the helmet first, and then from then on, we thought of like various ideas like such to implement in the future.
Good. So I just want to thank you for your presentation.
Yeah, thank you.
Thank you, guys.
Thank you.
For my project, I do the uninterrupted power supply. The main abstract for this project is to provide instant backup during power failure or main outage. And the UBS will notify the user when the power is out, and the device we're building will support all household device where there is power outage and maintain at least 1 hour of usage during the brownout or blackout. There will be battery indicator that will show if the battery is fully charged or charging or will need to be replaced. So our objective is to provide instant backup during power issue and notify user when there power outage, so they're able to save data on their computer before exiting. So we will use charger to convert from AC to DC using rectifier, then convert it back to AC with inverter. We will get some type of modified sine wave output to power the device, and smooth repetitive oscillation for AC power, and have a USB charging port. So this is the title page for the uninterrupted power supply. The main abstract, I already go that one. So the main abstract is to able to save data before the battery go out or during the main power issue. And this is the objective. The block diagram. We're having charger going to charger control so it doesn't overheat, overcharge the battery, and the battery will go into inverter, and the inverter will go to the load. And this is the inverter schematic. And the inverter component and PCP. And inverter component, I used the IC 4069 connecting to the MOSFET to control the on and off, to have like the current going to the primary of the transformer, so that it's have like the to have like a alternating current using PC12 as digital control to create a square wave from signal on and off switch from the MOSFET. And I use LM358 as dual op amp to swing from the polarity, positive to negative, and some capacitor to generate frequency for the alternating current, also to smooth the power flow and smooth the voltage. And I use the chain over relay for the secondary voltage, which is the out will be going to the load. So here I'm like my inverter setup for and try to have a test using a lamp, but it doesn't work at first. Here the indicator, which show the voltage, current, power, but there's no load right now, so there are no current. Just testing to see if it works. And I have to connect to a sun to get the current, to measure the current. This the sun. I have to connect like from a negative terminal to the sun of the battery, negative battery of the inverter as well. So it should be like in series to get the current. So I use the solar charge controller to charge the battery. Here I connect the battery to the inverter and take the measurement. The final product, able to get the inverter to work and charging. This is what the final product would look like. And the conclusion, I was able to provide like instant backup power, but I wasn't able to charge it because the battery is 100 amp hour. So it takes at least like 50 hours with 2 amp from the solar charge. So that wasn't good. I still need more testing for the charger. I use the portable charge, which is 5 amp, and it still doesn't charge. Since we designed this one for the computer, we need like better charging for the batteries. I try to use like a transfer switch, which will use the batteries when the power go out, but that will like have some delay. So that could cause the computer to shut down. So, or yeah, so I don't know if that's gonna work. So for the future, I think we're gonna use like a smaller batteries, so it charges faster and easier to move around, because this battery is around like 50 pounds. Here's some references. And I think that's it.
Okay, thank you. Does anybody have any questions? If so, please type it in the chat and I'll convey it to William. So I have one question while people are typing. Do you think you have any idea how you could fix the issue of charging? Do you have any possible solution that you could have tried?
I try to use like the laptop charger, which 5 amp, and it still doesn't work because the battery is, the capacitance is too big. So maybe using some power charger for it. Because it's take a long time to charge with like 5 amp.
Okay.
Because in the market, like we will only use like small battery, so it charge like quicker. But even though like they use small batteries, it will take like at least 10 hours for them to really charge the battery to the full. So.
Okay, that makes sense. Yeah. All right, William, I don't think we have any comments or questions, so I just want to thank you for your presentation.
Okay.
Okay, good morning, everyone. My name is Kyle Fuji.
I'm Matthew Arona.
And I'm Ryan Uribe.
This is our autonomous vehicle, our autonomous tank. And we're from the electrical engineering department. Our first slide will be showing our poster board that we created for our project. Each topic will be discussed further in the slides, but we wanted to show you what we've done as a whole. For our abstract, For our abstract, our objective for this project was to create a fully automated tank that will be able to self-navigate, identify, and destroy its targets. We wanted to successfully integrate hardware, software, and control theory and explore the capabilities of machine learning and its applications in the world. For the constraints of our project, economically, we wanted our machine to be relatively inexpensive so that it can be easily deployed by a number of potential government agencies. Environmentally, we wanted it to be able to move freely across a variety of different environments, to be pretty versatile. And for manufacturability, we wanted the device to be easy enough to manufacture so that the costs remain low. We also wanted it to be modular so that the design could be changed depending on the needs of different clients. And as far as health and safety goes, we definitely wanted to make sure our code was solid and smooth so that the vehicle wouldn't be targeting anything it's not supposed to. These are the standards that we followed for our project. The first standard is the standard for rechargeable batteries for portable computing. The second is the application of electric motors in Class 1 Division 2 hazardous locations. And the last standard was the vehicle autonomy, which is pretty much the ethics of artificial intelligence.
So for the software portion of the project, we loaded TensorFlow and OpenCV onto a Raspberry Pi. This is basically the brain and what allows the tank to achieve autonomy. TensorFlow is a machine learning open source software that allows you to train models so that your vehicle will be able to identify different things that you train the model to be able to distinguish from background using things such as convolutional neural networks and image recognition. And then OpenCV is another software that is utilized to allow cameras to be able to identify objects and set them apart from different environments and things like that. So this is our OpenCV working. On the left, we used OpenCV to detect we used OpenCV to perform lane detection. So the way that our tank works is it's following a track right now, and OpenCV kind of keeps the tank in between two black lanes. So in the left picture, you can see that we laid out electrical tape, And the green is what OpenCV is seeing as open. So it's allowing the tank to move along that point in the table, and it'll keep it in between those black lines. On the right is object detection with OpenCV. So you can see it's kind of hard to make out the writing, but it's 84% certain that that's a person taking the picture, which is me. And then behind me is my couches. So it's 80% certain that those are couches. So this is just a couple of the things that OpenCV allows the camera to see and detect. And when the tank is moving, it's constantly making these predictions and giving different levels of certainty to this object is this object is that. So that's kind of how the eyes work of the tank. So this is a graph showing how we trained the model for our TensorFlow. We trained it to detect balloons because we wanted the tank to be able to identify balloons in a room, point the laser at the balloon, and take a picture of the balloon to send it to us. So in order to do this, we needed to train our TensorFlow model. The top graph shows when we started training it, the uncertainty was very high and the loss was very high. But as the loss starts to exponentially decrease, our accuracy started to exponentially increase. So they're inverse graphs of one another, which means that as the tank is learning, the loss of data and information is going down. We used Google Colab to train our TensorFlow models, so which basically allowed us to access Google servers, utilize their graphics cards on their end and train these models because these convolutional neural networks take a lot of processing power. We also wrote a backend server that allowed us to secure file transfer photos to our mobile devices. So once the tank takes a picture of its target, it'll secure file transfer these photos onto our phone, and we get to see what the tank sees in terms of, was it an accurate hit? Was it a misfire? And this is kind of how we were able to calibrate what the tank is seeing and how accurate it was. This is the block diagram, our essential setup for the tank. So the middle part, point A, is the actual vehicle itself with the tank body. B is the Raspberry Pi. So this was the brains of the tank. C is our power supply. We just used the standard lithium ion battery, a LiPo battery. D is our pan tilt system. So we have a mounted pan tilt camera and a laser attached to the top of the vehicle, which allows the camera to move on its, so it has 2 degrees of freedom. It's allowed to look up and down, left and right. It's constantly surveying the room. So as it's moving, the camera's consistently slowly moving back and forth, up and down, looking for its targets. What else do we have here? We didn't use E. Our E was a TensorFlow processor. We didn't need it. It's basically a modular GPU that you can plug into the Raspberry Pi that takes the image processing and kind of offloads it a little bit. So you're not putting so much work on the Raspberry Pi CPU since it doesn't have an onboard GPU. So we didn't need that because our project actually didn't use too much of the Raspberry Pi's RAM. G and F are the laser and the camera. So that is what allows the tank to look around and see. And then the laser is what allows us to know that if it had something on it, it would be able to identify and point at that target.
So this is our basic wiring schematic. We have the Raspberry Pi connected to a battery for its supply because obviously this thing has to be mobile, so it can't be running off of a normal power supply. And then we have an electronic speed control hooked to the Raspberry Pi, which controls the speed and direction of our motors for our tank. Then there's 2 servos also connected to the GPIO pins of the Raspberry Pi. These servos are to control the pan and tilt motion of our gimbal camera mount. We also have the infrared camera sensor mounted as well, which is also connected to the Raspberry Pi. Then the laser is connected to the Raspberry Pi for control, but is fed power through a relay system. We had to add relays in order to supply enough power to both the laser and the cooling fan that keeps the Raspberry Pi cool while it's doing all these computing. So then there's a little bit more advanced stuff on the relays. The relays allow the Pi's low voltage GPIO pins that only output about 3 volts to control the higher voltage for the because we have a LiPo battery connected to the relays, and the LiPo battery gives us a full 7.4 volts. So now instead of only outputting 3 volts to the laser and the muffin fan, we can output the full voltage of the battery. And these relays are actually capable of switching up to 30 volts at 10 amps DC current. This allows us to keep the power at a much greater amount than if we were to just use the low current, low voltage of the GPIO pins. So, and then this is what our tank looks like at the end. It's sitting on the floor, plugged in, and we're testing it currently to see how much it can actually do and how its full capabilities. This is its completed form. We have to custom make aluminum mounts for the battery, as well as the camera and laser and the muffin fan, because we were going to 3D print, but with the school closing, we lost access to the 3D printing software and unit. Here's a couple of demo videos of just the tank starting to move around. Some very basic test code just to see how the motors respond and their speed, direction, things like that. And then here's a video of the testing the gimbal and the laser system on the relays. Again, a very simple code just to make sure everything's working correctly.
And then in conclusion, we were all very proud of what we were able to accomplish during this interesting time for the semester. We weren't able to accomplish exactly what we wanted, what we set out to do at the beginning, but we still felt like we were able to do a lot. Thank you for listening.
Yeah, and that completes our presentation. Does anybody have any questions?
Yeah, if you have any questions, please type them in the chat and I will convey those questions to the team. I just wanted to say that it's a really great project and you did a great job.
Thank you.
Thank you.
Thank you.
Somebody just said a comment that they're proud of all the teams. I just wanted to ask how much of a learning curve was it for you to learn about TensorFlow and all those software packages?
For me, helping out with that, I didn't have as much background with like programming and coding, so I had to research a lot to catch up, but it was all very interesting, and so it wasn't too bad. There's a lot of helpful articles and stuff to read online.
Yeah, that's a really good background to have right now. Machine learning is very popular.
Yeah,
David Chang,
sorry.
Dr. Chang said another great teamwork. Any other comments or questions? So were you, I have a question, were you able, I know given the situation is hard, but were you able to kind of do some kind of testing on how accurate it was?
Yeah, so that model that I showed you from, or that we showed you from the training graph, that is us training the TensorFlow model. So that's the theoretical how accurate it was. But when we actually look through the Raspberry Pi's camera and we can see a live video of how the percentages that it gives different objects of what it thinks it is, and they were all, so in the picture that we had, that was our first training model ever. So it was 80% sure that it was a person and 80% sure that it was a couch. By the end of it, we were able to get those numbers up into the 90s every time. So the more data you give it, the better it gets. So we didn't have too much experience with TensorFlow, and it was kind of rough, and we're just scratching the surface of these machine learning algorithms and the object detection and stuff. So I know that there's better and more efficient ways to do it, but from what we had and our resources available, I think it was pretty good.
I have another question. As far as the training, how did you select what data to give it, or did you just throw a bunch of data at it? Like how did you know what to train it with and what not to?
So Google Colab is pretty cool because it has these packages where you can search for images, or you search for whatever image you want to train it with, and it'll have a folder with thousands of those images inside of it. So then you feed it to your data model. And then, so we didn't have to hand pick these pictures. These pictures were already in models, and then you feed them into your machine learning algorithm, and then it trains it for you. So it was pretty much just hand picking what you wanted it to see, and then giving it to the model so that the model can train itself.
So what if you encountered a object that it wasn't trained for? What would happen? Do you know what would happen in that situation?
It would just disregard the object. If it doesn't know what it is, if it notices something in the background that doesn't match itself, so let's say we have a chair against a flat wall, it'll put a rectangular box around that chair, and then the way that the convolutional neural network works is it doesn't know that it's a chair, it just looks at objects in the chair. So it'll pick it apart by pixel, and then does it know what it is? No, then move on. But if it does know what it is, then we're a percentage certain that it's this object based on what we've seen before in our object training models.
I'm sorry, can you repeat that? I couldn't hear your response.
Which part didn't you hear? All of it?
Yeah, all of it, sorry.
Okay, yeah, so if it sees an object, it doesn't know what that object is. Even though it says chair or couch, it still doesn't know that it's a chair or a couch. It picks it apart pixel by pixel and sees that if it matches anything that it has, and it's already been trained for. If it hasn't been trained for it, then it disregards it. So it'll rectangular box anything that stands out in the horizon.
Okay, I don't know if anybody else having this issue, but I can't hear the response.
I hear you okay, Matt. But...
Oh, okay. Other people are saying they can hear you. Okay.
Yeah, I can hear just fine.
Essentially, I don't know if you can hear me, Professor, but essentially he was saying if the object isn't trained by the machine, then it'll just disregard it if it's not something that we programmed it to look for.
Somebody typed great job. If you can hear me, somebody said great job. Dr. Chang said another great practical team effort, teamwork. I also wanted to say that Dr. Chang informed me that the energy bank project couldn't be here because they had to be they were evacuated by their government yesterday, and they're on their way back. So that's the reason why they couldn't be here. Hopefully you can hear me. I just want to thank Kyle, Matt, and Ryan for their project.
Good afternoon, everybody. My name is Sharif Gobran. Today we're presenting the Internet of Things water flow sensor. We did this project under the supervision of Dr. David Chang. I have my team members here with me, Fadi Edward and Kevin Breen.
All right, I'll start with just giving an introduction of our design. But before that, I will just start with some facts. It's a water damage facts from insurance industry research. Based on the research, it says that 14,000 people in the US experience a water damage emergency at a home or work each single day. 98% of basements in the US will experience some type of water damage during their lifespan. $2.5 billion that's the annual cost to insurance companies from water damage in the US, and the average claim for water damage is $7,000. Actually, it starts at average 3,600, and it goes up to 26,300. So those are just some numbers from water damage. So our device is, the design we decided to go with, it's an IoT device that monitors the water flow inside a water line, and it sends the data over a Wi-Fi module to an open API, and it detects water leaks. The data from this device gets integrated with other data from similar devices, and those devices can be handled through an AI algorithm to be more efficient. And the device includes a shutoff valve that can be activated remotely using a Wi-Fi module.
All right, in our research phase, we examined a couple of existing products that are similar to our design, figure out what they were doing, what they weren't doing. We've identified some of them here. So we decided to implement not only the features that they had, but some additional features as well. Most of those products were only a shutoff valve or a flow sensor. We wanted to have both features in a single device. We also wanted to be able to integrate our device with any open API so that you could control it with anything you wanted. We also thought that a modular design would be nice, so you could integrate this into any pipe of any size for water primarily or for gas. And we felt that a node-like structure with multiple devices would give you more control, and that was something that none of these devices offered.
So this is the design we decided to go with because of its modularity. If we need to make any changes to the product, it can be done with minimal adjustment to the code, and it will have the same functionality. For example, if we design our project to, we actually designed our product to be using a battery and a solar panel. In the morning, the battery supplies power to the product and it charges the battery. And at night, or when there is no sun, the battery takes over. So let's say this product will be installed in the basement or somewhere where there is no access to window or sun. So we can just replace the power module and use AC power instead.
In our design phase, we identified a couple of constraints that we wanted to fit to. So we felt that a $200 price point would be competitive compared to the $200 to $300 price points for the existing products. We also identified that modularity that we keep talking about. And we wanted minimal power so that it could be used anywhere in the world, which is why we went with a solar panel. And we felt that just to maintain manufacturability at a large scale, we needed to choose components that would be widely available.
And we had to follow the standards. So when we were designing the product, we followed the Wi-Fi standard and the power and frequency and the rechargeable battery standard.
This is the first design, the schematics that we came up with for our microcontroller. Sorry, I skipped one slide. As you can see here, we're using the 80 mega 826. I think it has 28 pins. 12 of those are general input and output pins. We designed we specifically choose this microcontroller because it fits in our power profile, and it has enough input output pins to deliver all the features that we were trying to implement. We operated the microcontroller at a 16 megahertz frequency. I'm not sure if you can see in my mouse, but this is the crystal that we used to operate the microcontroller, and we added a couple of headers for the peripherals. The peripherals being the sensor, the shut-off valve, and the serial communication between the microcontroller and the Wi-Fi module. We had to make a decision on how to design our PCB because we were facing a price decision basically that we had to do. If we had a multi-layer PCB design, we had to ask an external company to print it for us because we didn't have the equipment, nor the school had the equipment to print multi-layer PCBs. We ended up deciding to just do one-layer PCB, all the trace etching instead of actually printing using a printer, because that was a cheaper option, and we still achieved the same results that we wanted. You can see here, this is the microcontroller header. We used two mechanical relays to operate we had to operate the controller and the sensor, so that's why we used the mechanical relay. This is just some snippets of our code that we used. We had to design 3 different Wi-Fi modules to be able to communicate with the microcontroller and send the data to the external API. Chose to design our product in a modular way. So we could have included the Wi-Fi with the microcontroller, but we chose to break it this way so we can have different implementations of the same design with very minimal code. I know you can't read anything here, but this is just for you to observe what the environment we had the intentions of this, so we can have the whole design in a one body, one small enclosure, so we can compare it with the existing products on the market and see how big or small it is. But unfortunately, due to the recent COVID-19 issues, we lost access to the 3D printer and we were not able to finish the design on time. You can see here this is the solar panel, this is the battery, and we have a controller here that supplies the battery when the solar panel is generating power. When it's not generating power, the battery is just feeding the microcontroller and the Wi-Fi module. And this block is just the sensor and the shut-off valve. This is our PCB, and this is the power module, and this small thing is the Wi-Fi module. We were able to get results. This is the sensor. You can see the timestamp and then the rate. I think it's in per hour. And just to use the device, and it's loaded. I just tested. Okay, I'll be able to show the video now.
Okay, I think Sharif was cutting off, and yeah, he's back. Okay.
Sharif, you're muted.
Yeah, you're muted. Okay. Okay, I'm muted.
Okay, can you still see my screen?
No.
So I'm not sure where I was cut off. Did you guys see that part?
Yes.
Yeah,
Okay.
I lost you when you were trying to do the video.
Okay. So this is a demo video of what we were able to achieve using this device. This is the sensor and the shutoff valve. This is just my laundry bucket. You can ignore that. This is the battery, the solar panel. And you can see here, it's the picture is not very clear, but you can see the data being fed to the API here from the sensor. And then I switched to the control to turn it off. And once I turned it off, you can see the water is still dripping here. So we didn't just cut off the power. We actually turned off this device, turned off the path for the water. So the water would shut off.
Here's the timeline we're following. In the middle, we were not really following the timeline because of the COVID-19 issue, but we were able to get back on track, and now we're on track, and everything is we're gonna be on time.
And here's our budget. You can see our total came out to about $250, which is over the $200 we were aiming for, but there is some redundancy and inefficiency here. So we believe that the cost for a single device would fit within our $200 constraint.
Quick comment, actually it was $64. We had to buy equipment in bulk. So for the relay switches, we had to get 10 of them. We couldn't just buy the equipment on its own. So with the amount of equipment that we bought, we can design four of these devices. So I think the price was, after we did the calculation, went down to $64 or $65. So in conclusion, this is a proof of concept or a pilot project to demonstrate what we can achieve using a device like this with the specific design that we chose. The opportunities for a middleware are limitless. You can do anything you want with the data being fed from that device to the API. You can feed it to an AI algorithm that can make sense of where the leak is at a specific structure or a plant or an industrial plant, and then this will maximize the utilization of water resources. And if we choose to use that device for gas monitoring, it will also maximize the efficiency for gas usage. Again, due to the recent issues with COVID-19, our access to the labs were limited. We didn't have the same tools that we were initially planning on having. So we had to get rid of the enclosure design. Otherwise, it would look nicer without having the wires out in the wild and the environment, and the corrosion for the PCB will be limited. But we were able to at least prove what we were trying to prove with what we did so far and the demo video. This concludes our presentation. We would be more than happy to have your questions.
I don't know if you can hear me. I couldn't hear the presentation, so I apologize for that. If you can hear me, can you hit yes?
I can hear you, yes.
Yes button? Yes, okay, that's good. If anybody has any questions that they would like me to convey, please type it in the chat and I will convey it. So Dr. Chang said a practical low-cost design. Homeowner insurance companies will be interested in such a project.
Thank you, Dr. Chang.
Any other comments or questions? So Sean said, can this be programmed to detect differences in water utilization from a norm?
From what?
From a norm.
Yes.
Theoretically, yes, it could, but that was part of that AI that Sharif was talking about, which we did not actually do, but it's something we've thought of.
Yeah, our project scope was only concerned about the hardware, but the middleware that we had in our initial design was specifically placed there so you can see the opportunities and the potential of using this device with an external software. It can be an AI, it can be just a simple interface for the user to control separate devices. But with an AI algorithm, you can tell what's the normal usage on a specific, like if you leave it working for a month, you can tell what's the normal usage, and then if it goes above or below, you would know that there's a problem, and you can implement more algorithms to have it turn on and off by itself automatically, or to just inform the user and then let the user take the action. Hope that answers your question.
All right, then somebody asked, can it be no, somebody commented, nicely done. Wow.
Thank you.
Somebody commented, Elizabeth commented, she enjoyed your project. She's experienced water damage from a broken hose on a clothes washer hose. So she can relate to this and it will help others out in the future.
Thank you, Elizabeth.
And then somebody commented, any next steps?
The next step would be working on that firmware, because it will fully realize the potential of the device and the way we intended it to function. And I think the very near future next step would be just design an enclosure to have everything protected from environmental damage and static noises and other factors that were not accounted for.
I think that was it for the questions. Hi, my name is Nancy Hernandez. I'm gonna be assisting John Fowler right now. And thank you for your presentation. You did a great job.
Thank you. Thank you for your time.
Hi, everybody. My name is Richard, and my partner's name is Isaac. And today we'll be presenting our magic mirror idea. And as you can see right there in our first cover page, you can see how our mirror did turn out, because that is our final prototype. Okay, so first I'll go over briefly our poster presentation we made. I won't go over every single detail here because some of this stuff we will be going more into detail in our presentation. But here you can see we had our objective, our abstract, standards and constraints, block diagram, and then right there you can see the Raspberry Pi schematic a bit. Now that isn't fully the Raspberry Pi schematic. Those are only just some of the components we use. So I thought about putting those because we use those. So you can see there's audio power, which we will use with our Raspberry audio. And then there's also component video power, which we will use for the camera and our TV monitor. And you'll also see the USB current limit, which we also did use for plugging in USB type devices. And then you could see our process. You could see how the Raspberry audio looks like right there on the top of the project design. And the camera is attached to it as well. And then that is the back of our monitor, and then the front again. And then the list of materials, results and conclusions and reference, we'll be going more into detail in our presentation. Let me see if I got this right. Yeah, sorry. Go ahead, Isaac.
All right, so basically our abstract is a smart mirror's key components consists of being a mirror, the monitor, and of course the Raspberry Pi. The Pi will be used to help display information onto the monitor, which translates into the mirror. In order to get the features onto the Pi, we need to download modules and configure them into our config file. Yeah.
And for our objective of our project is we want to create a user-friendly smart mirror. And by that, what I mean is we want to provide a mirror that can have several functions and capabilities. And some of these will be Wi-Fi capabilities, tell the user the weather updates, the time, and a daily schedule. And by that, the daily schedule, I mean their daily schedule that is linked to their phone schedule. So whatever they have on their phone for the schedule, it would also be incorporated in the mirror so they could see that on there as well. Message notifications that they get from their phone will be presented on the mirror, and several other more useful features. So we want to create a smart mirror that can be useful in our everyday lives while being very easy to understand.
So our project outline, basically the first thing that we had to do was research some things about the smart mirror, some functions that it had and what other modules that we can use. Then after that, we started doing research on like what parts we can use. And from there, we just started actually building the project and working on the code.
Okay, so some of the standards here you see are what we use for our Raspberry Pi and the whole project of the mirror. Standard IE 802, that allows us to incorporate the Wi-Fi into our smart mirror. Standard IE 488 allow us to use short-range digital communications. And then I did see someone raise their hand. Did someone have a question or anything? Well, I'll just keep going for now. I do see for standard ISO IEC 19794, that would allow us to use biometric data such as facial recognition, and IEE P1857 will allow us to use voice recognition software like Alexa or Google Assistant voice.
All right, some of the constraints that we try to incorporate is that we try to make the mirror itself pretty budget friendly, most likely within the range of like $50 or less compared to the competitors. Environmentally, we believe that the power consumption must be kept to a minimal and it should be durable. For manufacturability, it was pretty easy to get all the parts that we needed, and well, we ended up building the mirror, and that itself wasn't that hard either. And for health and safety, we decided to use an acrylic mirror, which is highly durable and higher quality than your average glass mirror. Mostly because like it won't break as easily. And I know because like I accidentally dropped it a couple times and it still survived.
And then some more constraints continued is, of course, like learning how to program on the Raspberry Pi, whether we use Python or Linux, will prove to be a challenge because coding can always be a challenge, especially when we code several hundred lines of codes, and then you have to find several different errors and debug the code, which can take a lot of time. Learning how to use voice assistant commands and facial recognition, as this will be our first time working with these two type of programs. So it was definitely a learning curve for us.
And then this is just a simple block diagram. Of course, the monitor needs to be powered up. The Raspberry Pi needs to be powered up. From there, it goes into like the camera and the audio. And then finally the mirror is, it boots up, and that's when we either be able to use the face authentication or the Google Assistant. And with the face authentication, it'll display your custom display, and if not, then it'll have a default display. And then for the Google Assistant, for it to work, we need to use a hot word key, in this case, smart mirror. And we couldn't use Google's like Hey Google, mainly because a software that's incorporated with it is no longer supported. So we had to find a different solution to that.
So for our project design, you could see there in the pictures. So pretty much is we got a two-way mirror, a frame, and a monitor, and we would connect the two-way mirror on top of the frame, and then underneath that we'd put the monitor in our, and then from the monitor with the Raspberry Pi, it would help to display the information onto the monitor screen, which will, again, like we said, will translate onto the mirror. So then here we would see that we'd connect the Raspberry Pi to the monitor via an HDMI cable. In our case, the monitor we were using did not have an HDMI cable, so we had to use a VGMA converter to HDMI cable to get through this process. The Raspberry audio, you could see there in the picture in the bottom left, that we just connect onto the Pi. It's very easy to do. And then we just had to set it up on the Raspberry Pi configurations as well as the Raspberry Pi camera on the bottom right. And then once the two are enabled, that's when we did have to learn how to program several programs or modules in order to achieve the stuff we wanted to have the two things to work with. Okay, then let me see if I can back here. Okay, so I will be showing the left video first. It's a motion sensor function. Okay, so here, this the motion sensor is we're just showing that it's going to turn off the screen right now, and that we just have it there to save power for our device when it's not in use. For the right side, you'll see the facial recognition part, right there. You'll see that the screen does change, and right there it changed, and it says, "Hello, Richard." So we did have facial recognition customized. And then I'll go over this as well. And then it's just more facial recognition. This is now my partner showing his face, and the screen does change with his face as well. So when he goes in camera, the background changes again. Okay. And then also, if you see on the right, I just added we just added some pictures. We just added some pictures of how the facial training worked. You can see on the bottom right, it says like strong, weak. Of course, that just depends on where the position of our face is at, whether it's on the side, if it's like not capturing your face well. And pretty much the main thing I wanted to take away from this is if you saw in every individual case of the facial recognition, each person that had their face on the screen had different screens showing, different programs. And with the facial recognition, we can allow the user to have which program they want to. So it gives very versatile use because each individual user can customize their screen how they want to. And Isaac, if you can take over.
Okay, so the first video that we're going to show, the song example, is just the start of the Google Voice Assistant and what we can do with it.
Can you sing me a song?
Wash, wash, wash your hands for 40 seconds, please. Soap will chase the germs away so you don't cough and sneeze.
And then the next video is basically showing you that it does more than just, you can ask a question. You can also add to your Google Calendar, and also, or you can just play it.
Yes.
At what time?
3 o'clock. 3 o'clock.
What's the title of the event?
Call a friend. No.
All right, my friend on April 30th, 2020 at 3 p.m.
Yes.
Do you want to save that?
Yeah, that's fine. Yes.
Sure, it's on your calendar.
And then that video also kind of shows that it's not the voice assistant isn't just specific to one person's voice. You kind of saw my partner responded to that one saying yes, and it was able to detect their voice. And then that last picture on the far right is basically just showing you that it does add it to your calendar at the very end.
Okay. And then I'll take over for the rest and just quickly go over the rest of what we have. So right here is the bills and materials and budgets. You can pretty much here we just listed all the prices of the materials we had and how much we spent. The total was $312.89. However, you can take away $80 from that from the poster board and printing, because we did have to design it on PowerPoint instead of actually print out the material itself. And then for our conclusion, in the conclusion, we have created a smart mirror that has several useful features. And then these features help to display useful information that can be tailored to an individual's specific preference. This project overall was mostly coding focused, which means it came with a lot of errors and debugging needed. Overall, we are pleased with our results and glad to see our project is functional. And then we just have a list of references of ideas and the setup. And that is our presentation on the Magic Mirror idea.
Okay, I just wanted to apologize. I was having some internet issues. Hopefully I didn't disrupt anybody's presentation. So thank you for that. So does anybody have any questions? If you have any questions, you can write it in the chat, and then Nancy will convey the questions.
Someone just sent us a message that the presentation was great.
Thank you very much.
Thank you.
Someone else said, good job.
Thank you.
Elizabeth said, nice presentation. And Dr. Chang said he loves the voice control.
Thank you, Professor. Thank you very much.
Thank you.
Taylor said he wants one now.
Same with me, I want one. And Dr. Chang said he also liked the face recognition. I would like to thank you for your presentation. Please don't forget to stop sharing your screen.
Okay, will do. Thank you very much.
Thank you. And that concludes track 2 of the virtual project showcase. I want to thank everybody for joining, and I want to thank all the presenters for presenting their work. All of it was really great. Dr. Chang said all was great, and he thanked me for being the host. And thank you, Dr. Chang, for all the projects that you submitted. All right, Nancy, do you have any other comments that you would like to add?
Thank you, everyone. You guys all did a great job. Thank you for participating, and keep learning.
Yeah, and everybody stay safe, and look forward to seeing you guys as alumni in the next project showcase. All right, take care.